Okay, so you guys are reading through chapter one this week, and this week the chapter is about mostly about air, and so it talks about air, mostly about air quality and what the nation has done with air quality, um, mostly over the last basically since 1970. Did you guys catch what happened in 1970? What important piece of legislation occurred? Nobody. That was the year the Clean Air Act came into being. That dramatically changed the culture of industry moving forward. So when before that law came into be, if you lived near oh um, let's say a waste treatment facility, you couldn't do anything to the waste treatment facility if they were causing lots of pollutants to be put into the air. There was no law against them doing whatever they wanted with the air. And after that, then they were responsible for things that they were putting into the air. Do you guys have any idea how that affects the environment here in the gorge? Especially in the Dalles, which is kind of weird because of its that geographical turn right there at the river, and you have everything boxed in by the two canyons. So during the summer months, it's obviously very windy here, and that's caused by the temperature differential between Eastern Oregon and Western Oregon. And then the opposite happens during the winter. But the issue, it's fine during the summer because most of the wind is really coming from the Pacific Ocean, which is pretty clean as far as wind goes. But then when it comes the other direction, east of us, does anybody know what's east of the gorge outside of the scenic area besides a bunch of windmills or wind turbines?
Don't really pay attention to what's east very much.
Okay. There's a besides the wind turbines, there is a coal fire plant that's run by PG&E, and there's also a couple of waste treatment facilities as well as a landfill out there. So when those vapors come in this direction, they can cause emphysema type issues with people specifically in the Dalles, because what ends up happening is the air gets stuck there, right there in the Dalles, because it's trying to get around that corner, that S loop, and it can't. So you have a buildup of a bunch of chemicals in the air that cause irritation to the lungs. So when you guys were looking at air quality things, there were certain things that there are standards now for, like ozone and nitrogen dioxide and sulfur dioxide, and then also the two particulate measurements, which are particles that are size 2.5 and 10. So once those came into effect, it was easier to track down where they were coming from and then make the responsible industries fix their problem, is really what it turned out to be. So coal fire plants before 1970 they just ran their smokestacks, and it was very black. If you were anywhere in the vicinity of one of those, you literally had to wash your house and your car because all the time, because you would end up having soot all over the top of your paint. So it would actually look like the inside of a chimney. And after that, they made sure that Clean Air Act made sure that everyone who was spewing stuff into the atmosphere made sure that the levels of which chemicals were being released, so these ones that I just talked about, that those would all be at a certain lower value. So you don't have black smoke coming out of the chimneys of coal fire plants anymore, because they made them retool how they burn the coal. So it really comes out clear and colorless because it's mostly just carbon dioxide. But tell me where coal comes from.
Oh, organic matter that died off thousands, millions of years ago.
Sure, and you dig it up out of the ground, right? So
Yep.
how clean is it?
Not very.
Not. So there's a term called clean coal, which was generated by the coal industry, so people would stop giving them a hard time about the fact that coal is very dirty. So one of the things that happens with coal is since it's just coming out of the ground, sometimes sulfur comes with it. So when you burn the coal, what you're hoping for is that there's no sulfur in it, but there is going to be sulfur in it. So you end up making sulfur trioxide gas or sulfur dioxide gas. Neither of these things you want. Let's let me try to share the screen and show you guys what you get with that. All right. So zoom in a little bit. So if your coal fire plant is burning away and it produces some, let's say, SO, I'll go subscript 3. So in this chapter, part of the chemistry portion of it is for you guys to learn how to say these names and be able to describe what they are or know the names and come up with the formulas. Have you figured out, any of you figured out yet how to name SO3? I'll take that as a no. So looks like on page, where is it?
Isn't that sulfur trioxide?
That is sulfur trioxide. You are correct. So the page I'm looking for has the prefixes mono, di, tri. There it is. Okay, so on page 36, there's a table 1.6, and that's telling you how to name compounds with when there's more than one of a particular atom there. So there's one sulfur there, and there's 3 oxygens. The only little caveat with this is if the first atom in the formula doesn't, if there isn't more than one, then you just go ahead and say its name. So the name of this molecule is not monosulfur trioxide, it's just sulfur trioxide. But if the second molecule was by itself, so what's a molecule you guys know that's by the second molecule is by itself? Everybody okay with this one? A couple of people posted a question about this on the forums. This is carbon monoxide. So the carbon is by itself, but it's the first one, so we just say carbon. But the second one is by itself, the oxygen, so I have to say monoxide. So this guy's carbon monoxide because there's only one oxygen there. If I were to put something in here, like oops, let's undo that. Let's say I put a 2 here and I don't know, a 5 here. Then the prefix for 2 is di, and the prefix for 5 is pent. Where should you know that pent prefix from?
Math with the pentagon.
Okay, so like if you know what the shape of a pentagon is, that would be good. Is there any famous building that has that shape?
The Pentagon.
The Pentagon. Yep, it's pretty easy. So let me stop sharing, and then I'll share this. And there you go. There is the Pentagon. It is a 5-sided building. That's where we determine what we're going to do as far as using weapons and whatnot, war stuff. Okay, so if we go back to this molecule, so I've got 2 carbons and I've got 5 oxygens. So then the prefix for 2 is di, and pent is for oxygen. So this would be dicarbon pentaoxide. That molecule probably wouldn't really be named that, but that's the that would be the technical name for that. So this guy up here is sulfur trioxide. In the atmosphere, sulfur trioxide could run into a lot of things, but one of the things that it could run into that would be inside your body would be this molecule. So if you're breathing sulfur trioxide into your lungs, it's going to pull that into the bloodstream, and your bloodstream is mostly water. And so the moment that those two things run into each other, we make H2SO4. Now, we haven't learned how to name this. In chapter 1, you don't even learn how to name this. This is for a lot later. But does anybody happen to know what H2SO4 is?
Sulfuric.
Yeah, it's sulfuric acid. This is one of the worst acids. So if you're in an area where there's sulfur trioxide and you breathe it in, you're actually making sulfuric acid in your bloodstream. That's a terrible thing to happen. So when the Clean Air Act came into being in 1970, sulfur trioxide and sulfur dioxide were two of the first things that were regulated, because we don't want that stuff to come out. So if it's sulfur dioxide, then this turns into S2O3, and that's instead of sulfuric acid, that's sulfurous acid, which is almost as bad as sulfuric acid. So these are not things that you want floating around in your bloodstream, and your body is not happy when that stuff goes in there. It sort of goes into emergency mode when it sees stuff like this to try to handle it, to get rid of it. Okay. So this chapter is a lot about clean air and the different things that you might find with air. Last class we were talking about what was happening in the gorge with the Eagle Creek fire, and so it was if you look on 28, there's a table that show table 1.4 and figure 1.9. Both of those things talk about problems in air quality with what's in the atmosphere, and we were in the very hazardous area for about 10 days last summer because of that Eagle Creek fire, because of all the particulate that was in the air. And if you're again on the book there, figure 110, which is page 29. And so we've got figure A and figure B. So figure A is just a little graphic of what can happen when you end up having something called a temperature inversion, which makes really bad, which makes the air stuck around where you are. And this happens in the Dalles. Every winter it happens at least a dozen times. And you end up with the picture B over there. So somebody who's outside the Dalles could be looking at the Dalles and it looks like it's all cloudy. But those aren't clouds. That's actually people's fireplaces and wood stoves. There were 2 winters in the early 2000s where I was asked to tell the radio station if people should try to not use their wood stoves and fireplaces. And it was during these temperature inversion days. So I'd check some weather reports and look at some diagrams and then let the radio station know that it was good or was not good for them to for people in the area to burn. But you, as just a regular person, can figure this out really easily. Does anybody know how you can determine if it's a bad day to burn just by going outside and looking around?
Well, it's like those days we usually smell it in the air.
Okay, one, it smells in the air. That one's pretty easy. Another way to do it, especially trying to catch it early, is if you go outside and you look and find somebody who's actually burning their wood stove, the smoke will be coming out of the pipe or the chimney, and it will rise at a fairly steady rate and be in a fairly straight line, and then all of a sudden it will make a 90-degree turn. What that 90-degree turn is in this picture right here, where it shows that warm air that's kind of blue. The smoke goes up, and once it hits that, it just turns sideways. It can't bust through that. So instead of that that smoke from your wood stove leaving the dowels, it ends up getting recirculated in the dowels and it just stays there. So the Dalles is actually a pretty bad air place, except during the summer when the winds are blowing nice and hard and you don't really have to worry about it. But
It's part of the reason why the Dalles is kind of called a dust bowl with our location.
I totally agree with you. It is sort of a dust bowl because the dust doesn't leave, it doesn't go anywhere. Plus, for being as windy as it is, it's a terrible place to kiteboard because that wind gets really, really squirrely. You don't really have any idea where it's going to go. It'll turn all the time because it keeps running into stuff.
I have a question.
Go for it.
My old notebook isn't showing me what you're telling me. So I think it might be a little bit different than the actual notebook, not the spiral one. Because the pages that you're talking about aren't the ones.
They're not lining up with what I'm talking about.
Yeah, when I go to page 28, it's talking about ultraviolet absorption spectra.
Wow. Really?
Yeah, and it's a lot of experiments, like pre-lab questions, part 1 of, I don't know, cooling water hypothesis, like a bunch of little like lab things. So I think
I think you have the wrong thing. I'm sorry.
yeah, it's the same picture. Maybe it's just like for like teachers or something, or I don't know. I don't know. It just looks.
There is a possibility that a particular teacher customized. So if an instructor wants to, they can call the publisher and say, yeah, I want pages 18 through 35, and then pages 98 through 67 or 167, and then they'll throw it into a spiral notebook. So I think maybe that's what's happened to you.
Yeah.
That doesn't sound
Okay.
good.
I'm probably gonna have to order the real one then.
I would send that one back.
Yeah, I'll do that.
I'm pretty sure. So like if we go over here and kill that, go to the front.
I might even like just go for the ebook if it's available.
The ebook. I did see that on Amazon. And,
How much was it selling for? Were they even selling the 7th edition?
I just had it. It was 21.
Oh, that's not bad.
That's how much. Yeah.
Well, this book brand new is 200. The newest edition, I think it's the 10th edition, was $228 or something like that.
Right. The spiral one is $32 and the printed one is $11. So I think I bought the wrong one. I think I bought the spiral one, not the printed one. So I'll just have to fix that myself.
Yeah, on Amazon, I'm seeing this book going for $5.50 for used.
Yeah, I'm looking at this right now on abebooks.com and it's $2.45.
Oh wow. Ebooks.
That was literally the first thing that popped up in Google. I went to the syllabus. Let me share that with you. So I went to the syllabus and I just copied this ISBN here, the ISBN 13, and then just pasted it into Google and looked for it, and that's the first thing that popped up.
Okay. So I have to order it. Yeah. Soon.
Yeah, because the ultraviolet stuff isn't even until chapter 2.
It must, yeah. It's like, right here, I'll read you. Does the title say, "What am I breathing"?
Yes. Yeah.
Okay.
It says the air we breathe.
Oh, this one says, "What am I breathing?" But
For chapter 1?
it doesn't say chapter 1. That's the weird thing. It just says experiment 1.
Oh, you have the lab manual that goes along
Oh
with this
my
textbook.
God.
Yeah.
That's the wrong one, huh?
Yeah, if this was a live class and you guys were coming to campus, we might use that lab book, but we can't use that lab book because there's a lot of stuff in that lab book that you wouldn't be able to buy at your house and use there. Wouldn't be safe.
Okay, well, at least we got that figured out. So,
Yeah.
good.
All right, let's pull up a periodic table.
Thinking, have you heard of the photographer Luke Wong?
Luke Wong?
Yeah.
No. Is he in the area?
He's a photographer in China.
Oh.
He's pretty much famously known for taking a bunch of pictures around full production facilities there.
Oh. I just looked him up. Huh. Cole. Maybe I have the wrong Luke Wong because these are all like pictures of people. Strangers on the street. They're pretty good. Wow, that lady's got some great hair.
I posted the photographer's name in the chat section.
Gotcha. Well, that's not even close to what I had. Oh yeah, that's much different than what I was saying. I have seen at least a half a dozen of these photos. Yeah, they're powerful. That guy going through the sludge in the river trying to push whatever he's carrying along with him. That one's freaky. Huh. Yeah, those are horrifying. Somebody needs to do it though. Yeesh. Okay, so what was I was pulling up a periodic table. All right. So let's share that. Do you guys notice anything about the orientation of the letters, the case of the letters? If it's a single letter abbreviation for the element, then it's just that one letter. And if it's a double letter abbreviation, then that second letter has to be lowercase. So the first letter is always uppercase, the second letter is lowercase. This kind of presents a little bit of a problem sometimes because if you're, do we know the difference between a serifed font and a sans serifed font?
No.
These are all serifed serifed fonts, meaning they've got like little lips and little edges to all of them. Let me go with the most classic one. My favorite font is Courier New. So every single letter, there isn't a letter that looks the same as any other letter. Does that make sense? How about I'll put chlorine in here again. Well, let's do, how about, there's an I, and then there's a lowercase l. And then below that, I'll do the same thing, I, lowercase l. But then I'm going to change the font. I'll change it to Arial, which is a very common font. Is that a problem?
Yeah, we're
I
still
can't
just
see the
in
letters that you were
table.
typing.
Oh, you're still seeing the periodic table? Oh, all right.
Yeah.
I'm sorry about that. Let me fix that. How about now?
Yeah.
Okay, so there's the word chlorine, and you can see that L and that I don't look anything the same. This is an uppercase I, and this is a lowercase l in Courier New, which is a serifed font. This is the uppercase I and the lowercase l in a sans serif font. So you notice like the one below it, it doesn't have any of the extra attachments to the top and the bottom. So the L and the I look exactly the same. What do you think the one looks like? Thankfully, it's a tad bit different, but sometimes that font, a font will show you a capital I, a lowercase l, and a 1 as all of the same font. So I'm telling you this because it really matters in chemistry, because that right there that I have, a C and a capital I, is definitely different than a C and a lowercase l. This is a molecule composed of one carbon and one iodine. And this is a molecule, or this is the element chlorine. Does that make sense?
Yep.
So make sure that you're aware of the font that you're posting, because it might lead the person to misunderstand what it is that you're trying to say. Okay. Let's share that table again. All right, so in this this section of the notes, it was also talking, or the text, it was also talking about the columns, which is also called the groups. So this column right here, last class, oh, maybe that was the live class. Okay, do we know what this element here is? Cu?
Copper.
Okay. How about Ag?
Gold.
Close. Gold is the one right below it.
Hey,
Silver.
So do these things have anything in common? These three elements?
They're not English. They're in a different language.
Okay, I do like that part, that they are in English, and we'll come back to that. But and at least the copper is close, but the other two are nowhere near silver and gold. They're all three of them are metals. Okay, that's good. Anything else?
the electrons, I'm guessing.
What about their electrons?
I was like, they're all pretty conductive.
You're correct. Silver is the most conductive element, and gold and copper are very close to being the same conductivity, which is why most wires are made out of copper. Unless the thing that you're using is very valuable, then they might make the wire out of silver, or at least the conductor tips out of silver or gold. If you were to crack open like a cell phone or something like that, you'd actually find a significant amount of gold coating a bunch of electrodes. Why is that? What cool property do?
From not heating up faster, maybe?
No.
I don't know.
No, that's not it. What well, what are those three things used for besides conductors? Have been traditionally used for?
Currency.
Currency. So if somebody gave you a coin to buy a chicken from you, would you want that coin to dissolve in your pocket? Or if you
No.
dropped it into a mud puddle, would you want it to start corroding? You wouldn't. So those three metals are three of the best metals at not corroding. And so that's why we've traditionally made them out, or those are the things that we've made coins out of, and also jewelry. I mean, not so much copper, but certainly the silver and the gold. So we're talking about this because that little column, those three elements are chemically the same, and that's why they're in the same column. So we move over a little bit. What do humans use chlorine for?
Water treatment.
Okay, so when you say water treatment, what is it actually doing?
Disinfecting?
Yeah, what is that? What does disinfecting mean?
Killing
Oh.
bacteria.
Killing microscopic organisms. It's for killing stuff. That's what it is for. Exactly. So, what do we use fluorine for? I know we don't use it in Hood River, but the Dalles uses it. Where do they use it?
Cherry processing plant.
Uh, I don't know. If they do, I'm unaware of that. It's a more widespread than the cherry processing plant. It's in the water supply. They fluorinate the water in the Dalles. The Dalles water tastes a lot worse than Hood River water. So why do they fluorinate the water?
Teeth healthcare.
That's a reason for sure. Main reason? What was the reason that we use chlorine?
Disinfectant. Kills things.
Same reason. So the water that you drink either comes out of a reservoir or comes out of a spring out of the ground. We don't do anything to it for the most part. There's nothing done to it. What I mean by that is they don't boil it, they don't filter it, they don't do anything to it. You're just drinking water that came straight out of the reservoir or straight out of a spring. And that might sound a little gross. It came straight out of the ground, but that's actually the cleanest water on the planet when it comes out of the ground. It's basically filtering itself as it goes through rocks, especially here where we live. Why? Tell me about the rocks around here. What do we have right here in Hood River County? What big object?
Well, with our area, there's a lot of basalt.
There's a lot of rock that has holes in it because of the volcano. So that volcanic rock acts as a filter. And so you can't get dirt and particulate into the water, and you can't get bacteria in it either because it can't fit through all those little cracks and crevices that the water goes through when it goes through the rock. So it's a great filter. So we actually have great water around here. But the Dalles decided they wanted to fluorinate their water for one reason or another. They voted to do that. And so there's much less chance of you getting some kind of infection from your water supply in the Dalles. The most common infection that happens from water is something called cholera, which is a terrible bacterial infection that causes you to have diarrhea for like 10 days. Obviously, we don't want that. It's not something that we see in the United States very often, but it's definitely something that that happens around the world. So, does it make sense that fluorine and chlorine are in the same column?
Yeah.
What do you think? Tell me about bromine's probable properties.
That can
Go ahead.
probably be used to kill things.
It can kill stuff. Tell me about iodine.
Definitely kills things.
You probably know for a fact that that stuff kills stuff, and it does. So why are they all in the same column? Because they react similarly. So every element, when you look at it in the periodic table, the elements above it and below it are very similar to the elements in that column chemically. So the person who came up with the periodic table, he was a Russian guy named Dmitry Mendeleev, and he figured out that what he wanted to do, we didn't have a good organization for the periodic table up until this point as humans. And so what he said was, what I'm going to do is I'm going to forget about organizing these things, element 1 all the way up to that time we were looking at like element number 83. And so what he decided to do was, yes, it does go, element 1 is the one in the upper left-hand corner, and element number 2 is the in the upper right-hand corner. So I have this row that I go across to 1 to 2, but they're not right next to each other. And instead what he did is he put hydrogen over the top of the lithium, sodium, potassium, rubidium, cesium, because those elements all did kind of the same thing. And so the fluorine, chlorine, bromine all got to be in the same spot in the same column because they all did kind of the same thing. The helium and neon and argon and krypton and radon, all of those things, they don't react with anything at all. So they got to be in the same column. That's why gold and silver and copper are all in the same column, because they don't chemically react well. They're very stable, and so we can use them for jewelry and use them for coins. Does that make sense? So everything in the same column, those react the same. Things that are in the same row, no, that's not the case at all. Things right next to each other might behave kind of similar, but they don't nearly react the same as things in the same vertical column. All right. So when we're putting substances together, we need to figure out naming. So we talked a little bit about the sulfur dioxide and sulfur trioxide, so let's go back to that. We come up with a nomenclature.
Yeah.
There are several ways to name molecules. In this first chapter, we're only going to talk about one way to do that. And that first way to do it is called a covalent naming. So naming compounds covalently is talking about what type of molecule that they are. And so a covalent molecule reacts things that are very similar to each other, and these guys are all called nonmetals, which I'm going to have to back up and pull up a picture of nonmetals. So let's go to EdPix 121, and then we go here. There we go. And we'll go here and we'll share that. All right, so forget about this ionization energy word. What we're going to talk about are the different colors that are here on this periodic table. Everything that's on this table that is salmony pinky color, those are all metals. Everything that's green, those guys are all nonmetals. And then the blue ones are something called metalloids, which is sort of like a cross between metal and nonmetal. So the first nomenclature that we're going to talk about is about green elements on this table reacting with other green colored elements. So if I look if you look on the periodic table, you should have a little black line that's more bold than the rest of the lines on the table. And that's differentiating between the metals on the left side and the nonmetals on the right-hand side. So let's go back over to that worksheet. So when you're trying to determine how to name something, the very, very first thing you need to do is, what kind of compound is this? And when I look at, say, number 3 here, I see something that's a nonmetal reacting with something that's a nonmetal. Or number 4, I see a nonmetal reacting with a nonmetal. A nonmetal reacting with a nonmetal. That means I get to name it covalently. And the nice thing about covalently naming stuff is, 1, we've already talked about it, and 2, it's the easiest nomenclature. The thing that you need to remember is those prefixes, so the di, tri, tetra stuff. So let me open something else up for you. This guy. Scroll down here. All right. Is everybody seeing this covalent naming thing?
Yep.
All right, so these are the prefixes that we were talking about before. So mono, tri, tetra. That one's probably not as easy to remember, but it's like a tetrahedral. You might remember from geometry class. And then penta we already talked about. Hex, like a hexagon. Hept is a weird one, but that one means 7. Oct we probably all know because of octagon. And non is 9 and dec is 10. So we won't go past that. There are ways to go past 10, but we're just going to go 1 through 10. And so if I'm going to name these molecules, right, or these substances here, let me just delete this out so we don't have the names. So this is a carbon by itself and a oxygen by itself. And we need to remember that if the first substance is by itself, then we don't say mono. So I look up here and 1 is mono, And so then I've got carbon by itself and then monoxide. So this is carbon monoxide. And the next one has 1 phosphorus and 5 chlorines. So how do you want to name PCl5?
Yeah, for the chlorine, it's pentachloride. So
The chlorine is pentachloride. And for the first substance, you just say its name and don't change anything about it. So then this would be phosphorus pentachloride. So with both of these first two examples, I said oxide and I think it was Shane said chloride. So what happens is the second substance in the molecule, I hack the end of the name off of it and I put that suffix IDE at the end of it, which you're probably pretty familiar with, like sodium chloride. It's not, table salt is sodium chloride, not sodium chlorine. And the stuff you exhale is not carbon dioxygen, it's carbon dioxide. So we're always going to be ending these names with the IDE suffix. So how do you want to name the next one, the N2O5?
Dinitrogen pentaoxide.
Excellent, dinitrogen pentaoxide. So saying that part right there is kind of hard because what you end up with is this right here. A double vowel sound in the English language is weird. So you can either drop the A or drop the O or use both of them. But it's kind of your speech becomes halting when you try to say pentaoxide. It just doesn't flow well. So if you were to look up the formula N2O5 and look up the name, this name would be there. The name without the A would be an alias, and the name without the O would be an alias. And all of those would be just fine because everybody would know what you were talking about. Okay, and then we've got the name here. So the last one is 1 sulfur. So I just say sulfur, and then it's a hexa, and then fluoride. And again, we can see that it says IDE at the end of all of these substances here. So why should you guys know this name here? Do any
Isn't it like a poisonous gas or something?
It's definitely a poisonous gas. Do any of you have a wood stove or a fireplace in your house?
Yeah.
You should absolutely have a carbon monoxide monitor. If you don't, you're risking carbon monoxide poisoning, which can kill you in your sleep because it has no smell. You breathe it in and you don't notice that you breathe it in, and then it ends up blocking oxygen from being absorbed by your bloodstream, and so you just suffocate without even knowing it. You just fall asleep and don't wake up. It's kind of scary. So any place that has like if you're renting a house and the house has a wood stove in it or a fireplace, the landlord is required to make sure that there's a carbon monoxide monitor in the house because they don't want to get sued for you dying because you didn't know that carbon monoxide was a possibility. All right. Also happens to be a terrible greenhouse gas. It's actually worse than carbon dioxide as far as greenhouse gases go. Alrighty, let's get out of this for a second and then hop back over to that nomenclature. So, somebody want to name number 21 for me? Well, that's a problem. Let's do this first. All right, somebody want to name number 21 for me?
What's S?
Sulfur.
Oh, okay.
Dinitrogen?
So far, so good?
Pentasulfide.
Perfect. Excellent. Nice work. How about 15?
Um,
Phosphorus pentaoxide.
Tetraphosphorus decaoxide. How about 12?
Disulfide. No, you're not.
You don't have to say the "ide" part for the first one. You can just go ahead and say the name of the element. So you're right, di, and then it's just sulfur.
Okay.
But the second one, you do have to put the IDE suffix. So what do you want to call the second element?
dichloride.
Yeah, so it's disulfur dichloride. Okay, so we're going with formulas and trying to come up with names. How about if we do the opposite? How about if we start with some names and try to come up with a formula? So what's the formula for number 12 going to be?
SD2. No.
Oh, that's
SO2.
11, but excellent. SO2 would be number 11. How about number 12?
Oops.
It's all right.
BF 5.
You're close. B is boron. This is bromine. Has anybody got bromine symbol?
Is it BE?
Nope.
BR.
Br. Yeah. B.
Oh, right.
So this would be BRF5. That would be the formula for bromine pentafluoride. So how about 13?
S2Cl2.
Perfect. How about 15? That one's a little weird.
AR4.
Close, but not AR. AR is argon.
Just A?
Nope.
A4?
There is no just A element. Oddly, that seems very weird now that I think about it.
Okay, AS.
AS, excellent. AS4, and then what? We're doing 15.
O10?
Correct. AS4O10. Perfect. How about, I don't know, how about 21?
N2S5.
Perfect. Excellent. Okay, good. Let's stop doing that. Alrighty, let's go back over to the other one. This guy. No. There we go. Does anybody know what that molecule I've got written there is? C6H12O6. It's a really important molecule.
A little bit of cheating there, going to Google, but it's glucose.
It's probably glucose. There's other things that it could be, but it's almost certainly glucose. So why is that molecule super important to us? What do we do with glucose?
It's the molecule that's used for energy in our cells, isn't it?
It is. We call that process cellular respiration. And so we use glucose molecules, and we eat glucose molecules, and then we breathe in oxygen molecules, and then we breathe out carbon dioxide molecules, and we also make water molecules. Okay. So I want you to think about what is happening to the glucose. So glucose, you can get it out of sugar, easy sources of it, breads like a donut or maybe mashed potato or something like that. So let's say that you ate some mashed potatoes. So that's going to be a lot of glucose. And that goes into your body, and your body's very, very happy about that. It breaks the starch down into the individual glucose molecules. And then we've got glucose running through the bloodstream, getting out to all the different cells, and then you can do things, like think and walk and read and do life stuff. So that potato that you ate has carbon and hydrogen and oxygen in it. How does the carbon get out of your body?
Carbon dioxide.
So how does it get out of your body? You're right, it is carbon dioxide, but tell me where it leaves, how it leaves.
Your respiratory system?
So you eat a potato, and the carbon in the potato leaves your mouth as a gas. Is that odd? The things that you eat, the things that you actually eat, metabolize, you exhale. The things that provide energy for your body. So this is a super important molecule for us because it's obviously providing us energy. But what else? What else thinks that the glucose molecule is super important? What other substance? What other thing?
Plants.
Plants. Why do plants think it's super important?
They reverse the process. They take carbon dioxide and water and make it into glucose for
Perfect.
them to eat.
So no, they don't actually eat it.
Okay.
They need a place. What do plants do with the glucose? Because they make lots of it. So they breathe in what we breathe out, absorb some moisture from the ground, and then make the thing that we're going to eat later on, right? We're all seeing that this is a nice symbiotic relationship. They make this, and we breathe that and eat that, and then we exhale this and urinate out that, and then they breathe that in and absorb that in, and we just have this nice cycle going on. So what is it that, so I'm looking out my window right now and I see a tree. What is most of that tree made of? This guy right here.
Okay.
Can you eat a tree?
If your body was, designed that way, it could, but no.
You're right. It would be nice if our bodies were designed that way, but it isn't actually designed that way. So the weird thing about it is that tree, the bark, the leaves, the grasses around the bush, that kind of stuff, all of those things are actually made out of mostly glucose, but we can't actually eat them. So does anybody have any idea why we're not actually able to eat them?
Nope.
It probably includes molecules that aren't consumable by the human body, so that are poisonous to humans, but other creatures are able to eat them. Because there's like deer or stuff that tear off the bark and eat stuff on the inside too.
Certainly. It's not that it's poisonous to us, because we Oh, that's a terrible image. Sorry. I'm looking for a nice picture of this. That one's not bad. Wow, that's really small. All right, let me share this. Okay, so do you notice that this is, well, you don't actually know that. The formula for this little ring structure here is a glucose molecule. This is a C6H12O6. So is this. So these are both glucose molecules. Every one of these little ring structures is a glucose molecule. This first one up here is starch. So the potato that you eat, or the potato chips, or the corn chips, or the bread, or the donut, or the bagel, that thing that you're eating is made out of starch. And all the glucose molecules are in a nice row like this. The bark on that tree or the grass, that's cellulose. And so it's still the same glucose molecules, but can we see the difference between the cellulose structure and the starch structure?
Cellulose is chemical chains alternating.
Yeah, the top starch, all the glucose molecules are, for lack of a better term, right side up. They're all facing the same direction. That C2OH is on top every single time. And on the glucose, every other glucose molecule is flipped over. We lack the ability to break that thing apart. So when you eat a potato, the first thing that your body does is it takes these glucose molecules and breaks them in half, breaks that bond right there where that oxygen is, and then breaks the next one off, and then breaks the next one off. It doesn't work here. We don't actually have the ability to do that. The way I liken it is we have a tool that can go in and unlock that. Just like you have a key for your car. But what if somebody were to take your car key and file off one of the little nubs on your car key? Would it work?
No.
No, it wouldn't work. And so the situation is we don't have the correct key to unlock the cellulose molecules. Other animals do, and somebody mentioned deer, and obviously anything that is an herbivore must be able to do that in some way. But we lack the ability. Can you tell me how that would probably change humanity if somehow we figured out a way to do that?
Well, for instance, grass, it grows everywhere.
So it grows everywhere, and so what would that mean for us as people?
Ready supply of food for most of the starving populace.
Yeah, starvation is over, right? You could eat anything that's growing on the planet. I don't have to kill and eat a deer that was eating the grass. I can just eat the grass. I get a lot more energy straight from the grass than I would get from eating the deer that ate the grass. There's a lot of loss along the way. So,
though it doesn't stop food companies from adding cellulose to stretch out food as it is.
I don't disagree with that. There's a terrible, it was probably about 8 or 9 years ago that a company that sold Parmesan cheese got caught dumping sawdust into their Parmesan cheese. People work. Say again?
I wouldn't doubt it because I think recently China, I mean, there's been stories that China's making like fake rice, and there's videos on Facebook of these little companies making all these foods like eggs and stuff out of like chemicals, which is weird. But
True.
I don't know. I saw it on Facebook, but yeah.
None of that stuff would be sold in the United States legally. And the company that was putting the sawdust into the Parmesan cheese got caught, and they went out of business immediately. So hopefully we don't see a lot of that.
I'm sure it's like people have heard of like timber workers eating like sawmill pancakes and all that. That was kind of a thing back in the day.
Sure. You can take the pancake mix and throw in a little sawdust, and then that makes you feel fuller than you are, but you can't actually eat it. So it's sort of like mixing in some celery with your pancakes, but it all tastes like pancakes, so it's all good. What would be the benefit of throwing in a little sawdust in your pancakes besides feeling a little full?
Fibrous.
Fibrous.
For the digestive system.
Yeah, you don't have to worry about being all stuffed up. There's no nobody has any constipation if you're eating pancakes filled with bark dust. Not that I'm not suggesting that, but it's definitely been done in the past. Okay, so here we are looking at this same molecule, this glucose molecule, in two different formats, and the molecule itself is germane to both plants and animals, and just the fact that you have an inversion between the two molecules. Okay, just one second. You have to leave. Sorry about that. My daughter wanted to come in and teach or show you a pig. I think that's what she had in her hand. The so we've got this glucose molecule providing two really important roles in both the plant world and the animal world, and animals are sort of locked off from it and they can't use it mostly in the plant form. It is kind of nice though that the plant does produce the starch for you, right? Even though the potato leaves are made out of cellulose, the potato itself is made out of starch. Does anybody have any idea why the potato plant would do something like that? Why does a cherry tree produce cherries or an apple tree produce apples? Why would it bother to use all of that energy to make that fruit?
Or
They could
foraging
reproduce
animals,
and
right?
spread.
Yes, you're both correct. The tree is hoping that some animal eats it and then poops it far away, so then we can get more trees way over there. So they're using us, not nearly as much as we're using them, but they definitely rely on us. Animals, that is. Okay. I noticed somebody found at the end of chapter 1 on page 52, there's a little blurb about a company that makes paint that has I'm sure you've all noticed when you open up a can of paint, you know that distinctive paint smell, that this company is producing paint where you don't get that smell, that it doesn't produce a lot of volatile organic chemicals because they've designed it in a way where the substances don't like to turn into a gas. And the company actually is out of Portland now. The only problem is their cans of paint are like $55 a gallon, so it's kind of rough. Okay.
And if you got a monopoly, why don't you just charge more?
Yeah, I think the chemicals that make up the paint itself, that keep it low volatile, are much more expensive than the traditional paint. So I think they're working on that. So, I mean, if we start as consumers demanding low volatility paints, then everybody will start making them, and then the price will come way down. But again, that's probably going to be off in the future a ways. Okay. Do you guys want to talk about anything from chapter 1 that we haven't kind of covered?
No, but I was just wondering maybe if the book would be available online, just so I could use it while the actual book arrives
I looked for it and I could not find it.
online, huh? So we're just gonna have to maybe see if the libraries have it, just while it arrives in the mail.
I know we don't even have any at the college, at least in the Dallas campus right now. They sold out from this class, and so they're gonna get some in on Friday. But I'm not
Okay.
sure how much the bookstore is charging. But
It's like they're charging like $30 for them.
okay,
The one that I got is used and it was $22.50.
at the bookstore.
Yeah, at
Okay.
the Dallas bookstore.
Okay. So knowing that the bookstores are a little light in the text, I'm going to end up pushing the due date on this first chapter one, the note taking for that. I'm going to push it back so nobody's going to be late with that assignment.
Okay. On average, like, what would you say the proper length is for that?
I've seen 4 pages and I've seen 12 pages, and I would say 12 is very not excessive, just very, very thorough, considering it's only 47 pages. So I don't know. It's the best thing to do is just do what it says on the guide, which would be to write down. We can pull that thing up. What was the problem? Let me share that. Huh. Did that just go away? Why'd that stop?
Yes.
That's weird. Okay. So just follow these 4 steps, just writing down the title of the chapter. So that's pretty easy. The figuring out what the main goal of this chapter is, and then for each of those sections within the chapter, write out the section title and then write a question that you think is going to be answered. So that's obviously the thing that's going to take most of the time. And then the other part that's going to be time consuming is to look at all the charts and all the pictures and describe why the author would have put those charts and pictures in the text. So that's it. Just follow those. You don't have to actually answer the questions that you're writing. Just write a question that you think would be answered by that particular section. So if it was talking about atoms and molecules, talk about what an atom. Like this would answer a question about what an atom or molecule is, or the table 1-6 that's showing you what the prefixes are. You would say what it is that the table's showing you and what it is that the person would get out of that. Is that helpful? Okay.
Easy enough to understand.
Okay. I think that's probably it, you guys. Does anybody have any questions?
No, just the book was mostly it.
Okay. Sorry that you got the lab manual and not the textbook, Marilyn.
It's all good because I ordered 2 of them. I don't know because I was doing it on my iPhone, so it's all confusing. I ordered that one and then I ordered the paperback, and that one's gonna get here April 10th. So I think that's gonna be the right one.
Probably. Probably. Okay. Well, you guys have a good weekend, and I'll talk to you guys next week. Message me if you have any questions. I'll go back to you.
Thank you.
Bye-bye.
Bye-bye.